Hello, welcome back. The title of this lesson is called Mass and Weight, and this is part one. Very important topic because almost every problem in physics has some sort of massive object. And of course we have forces involved, and so we have to figure out usually what's happening to the mass. And since we're usually doing problems on the surface of a planet like Earth, there's almost always going to be some sort of weight acting on the object. So, when you throw a baseball, or if there's a spring and some kind of mass attached to it, there's almost always a force of gravity, which we call weight of the object that we have in the problem. So here we're going to talk about what the difference is between mass and weight of an object, and also how to calculate its weight so that we can put it into all of these problems and solve them. Now, it's an easy concept, but in everyday language, we often confuse the terms mass and weight. So we're going to clear that up in the very beginning. Okay, mass. Mass of this marker has nothing to do with how much force I feel in my hand. Right? That has nothing to do. The force that I feel of gravity pulling down on this is what we call the weight. So weight is a force due to gravity, okay? But mass of this marker is completely independent of weight. Mass relates to how much matter is in the substance. So we all know that everything is made of atoms, and in the atoms you have electrons, which don't have much mass, but in the nucleus you have the protons and the neutrons, which carry almost all of the mass of an atom. So the mass of this object ultimately depends on how many protons and neutrons are in this thing, because the electrons don't have much mass at all. And so something made of lead has, atoms of lead, but the lead atoms have a lot more protons and neutrons, and so it has more mass. So when we take this object in deep space away from any gravitational field, it still has mass, okay? Because mass is the resistance to a force causing an acceleration. If you push on something in space, deep space, it has a very high mass, like a spacecraft, then you can get it to move, but it's going to resist your push. That's called inertia. So and if something has a very light mass, like this marker, if I push on it in deep space, it's going to move freely. So mass is an intrinsic property of every object. The more matter that's in there, more protons and neutrons, the more mass, and the more mass we have, we say it has the more inertia, more resistance to changing its state of motion. So mass has absolutely nothing to do with gravity, and everything, even if you take it into deep space away from any planets, it always has its mass. But when you take this object into a gravity field like Earth, the gravity pulls on. Of course, the more mass you have, the more it pulls down, and so that is the weight. The weight is the force pulling down by gravity, and of course, if we go to different planets with different gravitational fields, then of course, the force of gravity, which we call the weight, will be different on each planet. For instance, on the moon, everything has a weight about 1/6 of Earth's weight, but everything has the same mass. So, for instance, if I had a certain mass in kilograms on Earth, if I travel to the moon, I'll have the same number of kilograms of mass, because that's how many atoms and the types of atoms in my body. But of course, I would have a weight 1/6 on the moon as I do here. All right? So that's the difference between mass and weight. Keep it in your head. Mass is an intrinsic quantity that relates to the how many atoms are in there and the types of atoms, so the number of protons and neutrons. It relates to inertia. But weight is a force pulling down towards the center of a planet. So now we have to talk about how do we calculate this thing called weight, because it is something that we come up in every problem. So to start the discussion, let's recall, this is something that you should remember from the last lesson. We talked about Newton's second law of motion. F is equal to m times a. And these are vectors, so the force and the acceleration on any object are acting in the same direction. That's what the vector arrowheads mean. All right, so just as a picture, if I have some object, any object, some block, mass m, and I push on it horizontally with some force, horizontal, then some acceleration will be produced, and it has to be in the same direction as the force. That's because these are vectors, and so they have directions, and so the direction of the force always lines up with the direction of the acceleration that's produced by that force. But if we turn our attention, this is just pushing something horizontally. Now let's talk more about the weight. If I have an object, again, with mass m, and now we're not going to push on it, instead of pushing on it, what we're going to do is we're going to immerse it in a gravitational field, right? Then there should be some force acting down on this thing. right? So we're going to call it an F. It's an F, but I'm going to call it F sub G because it's sort of gravitational force. Or, you can actually call it, instead of F sub G for gravitational force, what we typically do is we call it W for the weight. But don't forget that this W vector, it's just a different letter, but it's a force. But we label it W because it's the weight of an object, but it's just a force pulling down, force of gravity pulling down, okay? So we have a force of gravity pulling this block down, right? And this block is experiencing some acceleration down, which is, we could call it acceleration A, but we know that actually in a gravitational field, we call it G. Now, we usually don't put the arrowhead on G when we were doing the equations of motion. We just called it 9.8 meters per second. But it is a vector. It's just that the acceleration G always acts down. Now, if you take up to be positive and down to be negative, then really G is negative 9.8 meters per second. But since we already know that weight always acts down, then you don't really have to put negative 9.8. If you put negative 9.8 here, then the weight is going to turn out to be negative. The negative weight would mean it's just always acting down. We already know that weight acts down, so you don't have to put the negatives in there. But that's, if you did put negatives in there, that's all it would mean, is that weight is acting down. So remember, the general idea for any force, I'm just going to write it again, is equal to mass times acceleration. But what we're saying is that when we're dealing with weight, the force is replaced by W, which we call weight. And that would be mass times whatever acceleration due to gravity, because everything accelerates when you drop it. So this becomes G, like this. And typically what you see is weight is equal to mass times gravity. You just drop these vector arrowheads. Even though they are vectors, the weight has a direction, but it always points down. The acceleration due to gravity is a vector. It always points down. But since everything always points down when it comes to weight, typically you just use this version of the equation. The weight of an object is equal to mass times gravity. This is, you're going to use it all the time. If I tell you how much mass something has, then you have to use it in a problem. If you want to know the weight of the object, you take the mass and you multiply it times the G, which is the acceleration due to gravity. All right. So what you will get out of that is you will get a weight in newtons. The mass will be in kilograms. And G, the acceleration due to gravity, is meters per second squared. Notice this is all the same stuff we learned before. Basically, all we're doing is we're applying Newton's second law of motion to an object that's freely falling. The acceleration becomes the acceleration due to gravity, and the force, we just rename it. We call it weight. So weight is equal to mass times gravity is not really like a new equation. It's not like something new. It's the same thing as Newton's second law of motion applied to a gravitational force. So weight is equal to mass times gravity. And what we typically use for the value of G here, we call it 9.8 meters per second squared. And if you're dealing in feet, feet and the English system, then you put a different value of G in there, but we never do that in physics. We usually, I should say more than usually, we almost always are using accelerations in meters per second squared, masses that are in kilograms, and when you have these units in these positions here, meters per second squared and kilograms for the mass, then the force, which is the weight, comes out in newtons. It's exactly the same units that we use for Newton's second law of motion, so there's really nothing new. All right, so let me just go through my notes and make sure. Since G acts down, the acceleration due to gravity acts down, then the weight also acts in the downward direction. We already said that. And weight depends on the planet's gravity. We said that. If we go to the moon, I'm going to weigh less. I'm going to have a less force of gravity, but my mass will be the same on both bodies because mass is an independent quantity relating to inertia, how much I resist the force applied to me in order to produce an acceleration. So what we have to do is, I think it's pretty clear that every object has a weight, and this is how you calculate the weight. But we have to talk about a couple of special cases before we solve a problem. And they're not hard, but let's talk about a special case. Let's put a table here. And this table is just kind of sitting on the ground, right? Like this. Just sitting on in a playground or something like this. And I put my object on top of the table, right? And this object has mass m. All right? So we all know from everyday experience that objects sitting on a table, they have a weight. If I hold it in my hand, it has a weight. Now, in general, we're considering the gravitational force all in this area to be the same. But technically, as you go very high away from Earth, the gravitational force gets less and less and less. So notice we say weight is equal to mass times gravity. We're not taking into account altitude or anything. If you're doing something more precise like a rocket launch where you're getting away from the Earth, we have more complex equations to deal with how the gravitational force gets weaker and weaker as you get away from the planet. So this is sort of an approximation of anything near the surface of the Earth, where we're assuming the gravitational acceleration is always the same near the surface of the Earth. The gravitational acceleration far away from the planet is a little bit different because, of course, as you get far away from the planet, then the gravity force falls off as you get a little farther away. Okay, so that's number one. But the main thing I want you to understand is that things have a weight when you're near the surface of a planet. They have the same weight no matter if they're stationary sitting on a table or if they're moving, if they're under free fall. This object right here that I've dropped, it has a weight, which is a force pulling down on it, right? And that weight is the same whether it's moving because it's under free fall or if it's sitting on the table. In other words, no matter how the thing is moving, it has the same weight. The weight is always there, always acting down, pulling down on the thing. And so on the table right here, basically what I will say is that there is a force which we call the weight acting down on this thing. And what is this weight? The weight is equal to mass times the gravity. So however many kilograms it is times 9.8 meters per second squared, multiply them, and I'm going to get a force in newtons. And that force is what is acting down. Now the reason the block doesn't go down is because it's sitting on a table and the table is preventing it from actually going down. But the weight, the force of gravity, is still acting on it even when it's sitting on the table. Okay, that's kind of common sense, right? But now let's take a different situation where we remove the table and let's put the block back in place like this. And what's going on here is there is exactly the same weight, right? The weight is still acting down and the weight is equal to mass times gravity. So if I remove the table, then what's going to happen is this thing's going to start falling, and these little lines mean it's falling down, or I could kind of like put some velocity, there as it's actually picking up speed as it's falling down. But the entire time, like let's say that you throw a block out of an airplane and it starts to fall down. Okay, as it's falling, it has the same weight, mass times gravity, right, as it does if it is sitting on a tabletop. So you can get into these trick questions. We're actually going to do one in a second where they try to trick you a little bit and try to make you answer incorrectly. The weight of an object, I want you to burn it in your mind. The weight of an object near the surface of the Earth, it doesn't change. And it certainly does not depend on how the object is moving. If I throw a baseball, then of course I overcome its weight I give more force in the upward direction so I can launch it in the upward direction, but the weight is still there and the weight doesn't change. If I'm able to launch it up, all that's happened is I've applied a force that's larger than the weight of the object, and that is what allows it to go up. But since the upward force is no longer there, eventually that weight, the acting down weight, will slow it down and then it'll reach the apex and then it will begin to come and accelerate down. But that weight, the downward force acting toward the center of the Earth, is always there. It never changes, and it's no matter what the motion of the object is, it is always acting there down. That's the punchline that you can get into trouble if you're not careful. So let's talk about that. Let's do a problem to illustrate that. And I hope, now that I've told you that so many times, you'll see right through this problem. But if I don't emphasize that, you might say, whoa, wait a minute. So let's read this problem. I'll read part A first, and we'll just go through and we'll have a few parts. The problem says, how much does a 138.0 Newton rock weigh when it is, and here's part A, when it's accelerating upward at a rate of 12.0 meters per second squared? Okay, so the problem is literally saying how much does it weigh, but notice they don't give you the mass. We don't give you the mass here. I actually tell you the weight of the rock, 138.0 newtons. I've given it to you in newtons, so that's already the weight, the force of gravity acting on the rock. How much does it weigh when it's accelerating upward at a rate of 12 meters per second squared? So you could draw a little picture. I mean, you don't have to for this particular one, but you could. I could draw a little rock. It's like a little oval right here. And what I have here is I have this guy traveling upward. So I'll just put a little up arrow next to it. And so the acceleration going up is 12.0 meters per second squared, right? And it's telling me that this force of gravity, which we call the weight, is equal to 138.0 newtons. right? Now I could calculate the mass here because I know that the weight is equal to the mass times gravity, right? So I know the weight, I could put it over here. I know the acceleration due to gravity, I could calculate how many kilograms the stone is. And that's what a lot of students do in the beginning. They're like, well, let me find the mass of the stone. Okay, I know it's going up at 12 meters per second squared, so let me calculate something here. But it's a trick question. How much does the rock weigh when it's moving upward at this acceleration? And I just got through telling you, it doesn't matter when I throw the rock down, if it's sitting on a table, if I throw it horizontally, if I do this, if I do that, if I do that. When it's near the Earth, the force of gravity is always acting down and it doesn't change. It's always there. So how much does it weigh when this object is traveling upward? Is another way of saying, what is the force of gravity on this thing, even though this thing is traveling upward? And the answer is that the weight is still 138.0 newtons. That is the answer. All right? And that is a little bit of a trick question because you think, well, let me figure out what's happening with the motion. All we know is that if this object really is traveling upward with an acceleration of 12 meters per second squared, we know there is a force pulling this rock down, the force of gravity, the weight of the object, okay? But if there was nothing else happening, the rock would go down, of course. But it's not going down. The rock is actually traveling up. But not only that, it's accelerating up. So that means that I must have some sort of little rocket engine or something pushing upward with a force that is larger than the downward force of gravity. To overcome the gravity and have a net force up, there has to be some force acting up slightly bigger than this so that I can have some sort of acceleration up. But that doesn't change the fact that the object's weight is the same. So the way the problem is worded, how much does a 138 Newton rock weigh when it's accelerating upward? The weight means, what is the force of gravity? That doesn't change. Yes, there must be some other force making it move up, but that's not what the question asked for. They asked for the weight. That's the main thrust of this problem. So now that we talked about its depth, we can read part 2. How much does a 138.0 Newton rock weigh when it is, part B, accelerating downward at a rate of 3.50 meters per second squared? Well, we already know the answer, but we can, of course, make ourselves feel better by saying, well, here's a rock, here's the weight, 138.0 newtons. Of course, I could calculate the mass if I wanted to, and in this case, the acceleration is actually going downward. And the acceleration, since it's downward, I'm going to label it as a negative acceleration, 3.5 meters per second squared. So how much does a rock weigh when it's accelerating downward? Well, the way to translate this is, what is the force of gravity acting on this rock, even when it happens to be moving downward at this acceleration? Right? Well, nothing changes. The weight is still 138.0 newtons because the force of the planet pulling down on it is what we call the weight, and that doesn't change no matter how it's moving. So we know the acceleration due to gravity is 9.8 meters per second squared down. But this object is not moving down at 9.8 meters per second squared. So what does it mean? Well, what it means is that if I had let go of this rock, it would be accelerating downward at 9.8 meters per second squared. But it's actually accelerating downward less than that. So there must be some other force that I haven't drawn here in this situation. Like, let's say there's a big current. Let's say you're standing at a cliff, okay? And you throw a balled up piece of paper, just a paper, not a rock, off of the edge of the cliff. It starts to fall down, but immediately an updraft of air comes and pushes it up, not enough to make it accelerate upward, but just enough to kind of like lessen the force of gravity, so to speak. It's still falling down, but not as rapidly as it would at 9.8 meters per second. So there has to be another force there somewhere. If there was no other force, it would go down at 9.8 meters per second. But because it's not, there must be some other upward force sort of cushioning it, for lack of a better word, that's making it fall down at a rate, but not a rate that of a normal gravitational fall. So we have some upward force here that's enough to overpower it, make it go up. We have some upward force here that's not quite that much, that just lessens the downward acceleration, but you get the idea here, right? So, but the weight of the object in both cases is the same. All right, now let's change it up. Part C. How much would the rock weigh in situations A and B if it had a mass of 138.0 kilograms? kilograms. So what we're basically trying to say is in these two situations, in other words, where the rock is going up at 12 meters per second and falling down at 3.5 meters per second squared, instead of this being the weight, what if instead I just tell you the mass is 138 kilograms? What would its weight be there? Well, we know its mass. Anytime you know its mass, you can always find its weight. It's just mass times gravity, mg. And so if the mass were this, 138.0, and g is 9.8 meters per second squared, you have to have the right units. Kilograms for the mass, and g is 9.8 meters per second squared. You can write the units down if you want, but ultimately you just have to keep track of them. Make sure this is in kilograms, make sure this is in meters per second squared. And when you take 138 times 9.8, you will get a weight of 1,352 newtons, rounding. All right, this is the number of newtons. Now, this weight, I'll put W for part A would be that, and W for part B would be the same thing, 1,352 newtons. In other words, it's this, if the mass of the object were given by this many kilograms, then the weight of the object, if it's flying upward, and the weight of the object, if it's flying downward, is the same. So it's really the same as part A and B, but I'm just forcing you to calculate the weight there, just to get some practice there. All right, part D. This one's a little bit different. Let's say, how much would the rock weigh if it was traveling upward at a constant velocity of 23.0 meters per second? So it's not accelerating up or accelerating down. It's just traveling with a constant velocity. So what does this look like? Here's your rock. And now we're going back to the rock having a weight of 138.0 newtons. But in this case, it's not accelerating up or accelerating down. In fact, the acceleration is 0. It's not speeding up or slowing down. However, the velocity is in the up direction of 23 meters per second. So it's not accelerating. It's like a rock, for some reason, it's just going up like this. It's not accelerating or slowing down. It's just constant speed going up, right, like this. So what would its weight be in that situation? If its weight is given to you as this, again, it's independent of the motion. So it's a little bit of a trick question. So for part D, the weight will remain to be 138.0 newtons. Now, how could this situation actually arise? Of course, if the rock, we let it go and there's no other forces, it's going to want to fall down and it's going to accelerate down, right? But here we know that the force of gravity is 138 newtons. So in order for there to be no acceleration at all, there has to be no net force on this object. 0 net force. Because remember, F equals ma. So force is equal to mass times acceleration. There is no acceleration here because it's traveling at constant velocity, just a constant upward velocity, no acceleration. So if there's no acceleration, we know from F equals ma, we know that if there's no acceleration, there has to be no force. But we have a force here, a force of gravity. But remember, this force in Newton's law, it's the net force acting on the object. So there has to be a total net force of 0 acting on this thing to make the acceleration 0. So if I have a weight acting down of this much, there must be some upward force balancing this exactly. So there has to be some upward force exactly balancing the downward force to give me no net force acting on this object. It's the only way that it could, so you could kind of kickstart it in motion, and then there has to be a balancing force to make it not accelerate, and then it will just continue to move up forever and ever, right? At that, because remember, an object in motion tends to stay in motion like this. So we're going to get into a lot more problems later with sort of calculating how to deal with balancing forces. I'm just sort of talking through it to explain to you how these situations that we've drawn on the board work. But notice the common thread through all of the problems is that the weight on the object doesn't change. If the object is sitting on the table, it has a weight, mass times gravity. If the object is falling, it has a weight, which is the same number, mass times gravity, even if it's in motion. If the object is accelerating upward somehow, then it has the same weight that it has when it's at rest. If the object is falling down at a rate different than gravitational falling, then it has the same weight. That number doesn't change. If I change it so the object has some mass, I can calculate its weight, but that weight is the same if it's moving up or moving down. And if the object is moving up but not accelerating up, so it's just moving up at a constant speed, then of course it has the same weight as well. That's the main point of the problem. You need to separate in your mind the fact that objects have weight and then objects may be moving. Because when an object is moving, you have to, later on, we'll calculate the net force on the object. For an object to accelerate, there has to be a net force, but that doesn't change the fact that the weight is always there. Always. When you throw a ball, you can envision there's always an arrow pointing down, trying to change the path of the motion. That is the main thing you have to get from this. And the other idea that's critically important is that the weight is the force of gravity. It only is something that applies near a planetary body. But when you go into deep space, an object still retains its mass, which is its inertia, its resistance to changing its motion. So, watch this a few times. There's a lot of philosophical stuff in here that I'm trying to get across. Then follow me on to the next problem. We'll continue to build your skills with mass and weight.